When we build complex AI systems today, we typically rely on a specific architecture, a network of specialized agents, all managed by a central orchestrator. Here, the central orchestrator acts as the sole manager, assigning tasks and managing all communication. But as volume increases, this single gate becomes a severe bottleneck, creating massive data traffic jams. If it crashes, the system fails. Furthermore, adding agents creates unsustainable coordination complexity. Trying to engineer a smarter central planner eventually hits a mathematical wall. Scaling multi-agent AI requires a completely different architecture. Researchers from Harvard and MIT have proposed a solution that bypasses this central bottleneck entirely. They drew their inspiration from Friedrich Hayek's economic theory of decentralized market coordination. The thesis is simple: replace the centralized AI planner with a self-organizing agent economy. Instead of a hub-and-spoke system, agents are arranged in a decentralized mesh network. They interact directly with one another, with no central manager overseeing the process. This society is governed by three simple economic pillars: local auctions, wealth accumulation, and bankruptcy. By allowing agents to compete for the right to act and exchange payments, these simple signals drive planning and coordination entirely on their own. Without a central controller handing out the assignments, the immediate question is how any individual agent knows when it's their turn to act. Let's track a complex, multi-step task entering this decentralized mesh. It starts with a localized bidding phase. The agents adjacent to the task analyze it. Based on their specific training and their local view of the problem, they calculate a bid that represents their confidence in solving the next step. The agent submitting the highest local bid wins the right to execute that step. After completing its work, that winning agent takes the partially finished task and auctions off the next step to its own immediate neighbors. This entire routing sequence happens purely peer-to-peer. The system does not need to know the entire map of the network to move the task forward. By utilizing these localized auctions, the network distributes decision-making directly to its edges, completely avoiding the central bottleneck. But routing a task is only half the equation. The system also needs a way to evaluate agent performance over time, a concept known as decentralized credit assignment. When a long sequence of agents works on a single output, the system has to figure out which specific agent actually caused the final success or failure. In a massive decentralized network, this is practically impossible without a central tracker logging every single action. The solution here is physical currency. When a final output succeeds, the environment triggers a reward, delivering a payout directly to the final acting agent. That final agent then uses a portion of its reward to pay the agent that passed it the task. That capital flows backward along the exact chain of execution, with each node taking a cut. In this framework, an agent's wealth is simply the physical accumulation of these historical payments. This localized wealth directly solves the credit assignment problem. It acts as a pure mathematical proxy for how valuable that agent has been to the overall network. We can now look at how the total collective intelligence of this society adapts across thousands of tasks. This happens through economic selection. The system operates in continuous cycles of exploitation and exploration. During exploitation, high-wealth agents, those that consistently make good decisions, are duplicated. The system creates slightly mutated variants of these successful models. This allows the network to aggressively capitalize on effective strategies, refining them over time. The exploration phase handles the opposite end of the spectrum. Agents that consistently lose auctions or contribute to failed tasks drain their capital until they reach bankruptcy. Bankrupt agents are permanently deleted from the network to free up computational resources. To replace them, the system generates entirely new, random models and injects them into the empty slots. This constant influx of randomness prevents the network from stalling out in a local optimum. It ensures the society is always testing new approaches. Through this continuous cycle of creation, selection, and elimination, the population structures itself around the problems it faces. When you run these three mechanisms at a massive scale, you get the emergence of complex, multi-step reasoning. Agents organically specialize, pass tasks effectively, and solve problems from start to finish. But the coordination observed here is entirely a byproduct of local economic incentives. No central programmer wrote a rule dictating how they should organize. The researchers tested this architecture across a series of rigorous domains. The tasks spanned mathematical reasoning, financial research, scientific literature review, and even distributed system optimization. Even when initialized with weak, unspecialized models, the economic network consistently outperformed stronger, centralized baselines. Because there is no fixed structure, the topology of the system automatically shifts its layout to fit the specific computational requirements of whatever task it receives. We are moving from engineered top-down coordination to emergent bottom-up intelligence. The path to scaling multi-agent systems lies not in building smarter central managers, but in designing the decentralized economies they inhabit.